Hi, thanks, Ron. So I'm Sam from Berkeley. Feel free to stop me, ask questions. The first half of this talk is gonna be like some statistics 101 review, so bear with me. And then the second half is gonna turn into an algorithms talk. Okay, so the talk is about the simplest high-dimensional statistics problem of all time, which is estimating the mean of a random vector. Hi. Oh, Mike, thank you. Yeah. Sorry. I'm so noisy normally that I don't think of it. Okay, which is estimating the mean of a random vector. So the problem for the whole talk is you get to see IID samples, x1 through xn, from some unknown d-dimensional random vector x. And your goal is to estimate the mean. Okay, so the expected value of x. And just for purposes of this talk, I'm always going to assume this random vector is what's called isotropic, which just means its covariance is identity. All right, that's so it saves me some writing stuff out. And my goal is going to be threefold. I want estimators for the mean with what a statistician would call a strong non-asymptotic guarantee, and that just means that we'll be able to prove interesting things about it for finite values of n, instead of taking an n to infinity limit. I want to make very weak assumptions on the underlying random vector x, and we'll see on the next slide what that means. And I want polynomial time algorithms. Okay, so let's get a bit more concrete and address the elephant in the room, which is, why aren't you using the most obvious algorithm in the world, which is the empirical mean? It's very computationally attractive. It's easy to analyze. It sounds like a pretty great algorithm. Take your samples and average them. So what makes the empirical mean great? If you go back and analyze, in what sense is the empirical mean the best estimator? What you find out is that among all unbiased estimators of the mean, the empirical mean minimizes the mean square error, which is to say the expected L2 distance from the empirical mean to the population mean. Okay, so that's nice. It tells you something about what happens typically. Like this expectation is saying what happens most of the time in this estimation problem. But one thing it doesn't tell you much about, this kind of analysis, is what statisticians would call confidence intervals and I would call tail bounds. Okay, so I want to understand in this talk a more refined notion of an estimator doing a good job. I want to understand, for various values of t, what is the probability that my estimate of the mean deviates from the mean by some L2 distance t. Okay? And one reason you want to do that is because if that probability is less than some number delta, then you are 1 minus delta confident in a confidence interval of width t around your estimate, right? You say I report this estimate, and I'm 1 minus delta certain that the true mean is at most distance t away from my estimate. Okay. So my goal in this talk is going to be to understand estimators for which I can prove tail bounds rather than just understand typical behavior. Okay, so I want to start continuing to focus on the empirical mean. Let's try to understand not just its mean square error. That's the classical thing. I want to understand its tail bounds. How probable is it that you get something, that you make a wildly bad estimate by using the empirical mean? And let's focus on the dimension equals 1 case. So this is really classical stuff. Now I get just n IID samples from some univariate random variable with variance 1. And already in this setting, the behavior of these tails is highly dependent on what kind of assumption I am willing to make about the underlying random variable. Okay, so let me describe two contrasting situations. So one situation is that I'm willing to make a really strong assumption that the unrandom variable is Gaussian. Okay, so let's say it's n mu1, variance 1 Gaussian. And then if I average n IID copies of a Gaussian, I get back another Gaussian with much lower variance. And applying a standard Gaussian tail bound to that, I learn that the probability of a deviation of order t is decaying like e to the minus t squared n. N is the number of samples. So this is like exponentially good tail decay. Okay? This means that your confidence intervals are really tight. On the other hand, if you're willing to make only a much weaker assumption, let's say the variance exists and is at most 1. Right? So the third moment of this random vector might be infinite. Then if you apply Chebyshev's inequality, which is the best thing you can do, so the second moment bound on the tail, what you learn is that the tail is decaying like 1 over t squared n. So it's exponentially slower than this Gaussian tail. Okay? And if we just illustrate this in terms of confidence intervals, so I'm going to go back and forth between tails and confidence intervals all the time in this talk, so it's good to get accustomed to this. If I want to understand what width I can take to be 1 minus delta confident in my estimate, that width is growing logarithmically in 1 over delta in the Gaussian case, and polynomially in 1 over delta in this fat tail case. Okay, so there's an exponential difference in the quality of the confidence intervals for the empirical mean depending on what assumptions you're willing to make. Questions about this? Okay. So in this talk, when I say I want to make weak assumptions, what I mean is I want to allow for the case that the underlying random variable has only finite variance. Maybe its third moment already doesn't exist. Okay, this is a much, much, much weaker assumption than Gaussianness. So why would you do that? Well, I mean, it still allows for the case that your underlying distribution is Gaussian, like in this blue curve, but it also allows you to model lots of other interesting settings. Right? It could be that your data are corrupted. So corruptions in this green thing are sitting far out in the tail, and they could mean that sub-Gaussian tails are violated for your corrupted data. It could be that your data really follows some heavy-tailed distribution, like a power law distribution that we see in large random networks. So that's what's going on in this orange case. It could be that you just don't know. You don't have a good reason to assume your data are Gaussian, and so you would rather not do that and use some estimator which is robust to many situations. So this all leads to the question, still sort of in the one-dimensional setting, what if I'm willing to use an estimator that is not the empirical mean? Right? What if could I improve on the confidence intervals of the empirical mean by choosing some different estimator when I'm only willing to make this assumption that the variance of my underlying variable exists? So here's a really greedy version of this question, an extremely optimistic version of this question. The optimistic version is there some estimator mu hat in the setting of univariate mean estimation such that the probability that mu hat suffers a deviation of magnitude t is bounded by e to the minus constant times t squared n. So up to constants, this is the Gaussian thing. This is the Gaussian tail. Right? But only under the assumption, let's say, that x has finite variance. So unfortunately, the answer to this is no. There's an information theoretic lower bound that says you cannot do this. But I'm only 5 minutes into the talk, so probably there's some more going on here. And what's going on is that, in some sense, you can fake it. Okay, so I'm going to describe to you what fake it means. I'll do it via a theorem. So here's by now a classical theorem. We're going to see how to prove this later in the talk. The theorem says that given just a little bit of additional information beyond the setting I just described, you can achieve morally this bound. Okay, this exponential tail bound. What is the additional information? I need to tell you the confidence with which I want you to estimate. Okay? Or alternatively, I need to tell you the width of the confidence interval that I want you to achieve. So what does this say? This says for every deviation magnitude t, right? So I fix t ahead of time. There exists some estimator mu hat t. So mu hat t, what does it do? It takes x1 to xn, these samples, and it outputs an estimate called mu hat t. It's just a real number. Such that for this mu hat t, the probability that it suffers a deviation of size t is bounded by e to the minus constant times t squared n, so the Gaussian quantity. Okay, this is maybe a little bit, this business that I have to tell you t ahead of time is at first a little bit weird. We're going to see what goes on here later in the talk. But if you just if you squint your eyes and take a high-level view of this theorem, what it's saying is that as long as you're willing to commit ahead of time to how confident you want to be, right? And notice that, of course, if I commit to being very confident, I'm going to get a lower accuracy estimate. But OK, if I'm willing to commit ahead of time to how confident I want to be, then you can estimate the mean of a random vector with only finite variance as if it were Gaussian. You can get the same with confidence intervals up to constants. Does this make sense? Are there questions? So this is pretty surprising, right? Like we're going to see how to prove this later in the talk, but this is kind of wild because you're exponentially beating the empirical mean. So this leads to a pretty natural question. What happens when the dimension is bigger? Right? This was all the one-dimensional case. What happens when d is bigger? So
Actually,
yeah.
how does the empirical median behave in terms of
Good. Good. Empirical median is extremely high confidence. It's very well concentrated, but at best it estimates the population median. Right? If you take infinitely many samples and you report the median, you're getting the population median. And under the assumption only that the variance is 1, the population median could have distance constant to from the true mean. That's right. So actually, just to spoil the surprise, this is going to involve some kind of mean step and then a median step. This is a median of means estimator. So it needs to reduce the bias and then get some confidence out of a median. Excellent.
And just to make sure, when you say polytype computable, you mean in terms of polynomial in n and t?
Yes, I mean in n and t. That's right.
So right now it's 1D, I guess.
It's 1D, but it's going to become important later. Yeah, in 1D it's not so surprising you can do this. But okay, so what's going on in higher dimensions? Let's go back to the empirical mean, and I just want to tell you the same sad story of the empirical mean again, but now when the dimension is higher, right? So the story was the confidence intervals, now they're confidence balls, but I'm still going to say confidence intervals, that are achieved by the empirical mean are highly dependent on what assumption I'm willing to make, strong assumptions versus weak assumptions. So let's think about the strong assumption first. The strong assumption is that your underlying variable is Gaussian. Okay, so identity covariance. In the case that it's Gaussian, you can do totally standard stuff, and you can show this kind of inequality. So there's the probability you suffer a deviation of order t plus some startup. This is like the expected deviation in d dimensions, which is growing a little bit with the dimension. The probability you suffer such a deviation, it's bounded by this sub-Gaussian tail, e to the minus t squared n. And I want to emphasize for later in the talk that this tail is dimension independent. So that you can prove this by Lipschitz Gaussian concentration if that means anything to you, but if not, don't worry, this is true. And the point is that once you pay a dimension-dependent startup cost in your confidence interval width, becoming more confident does not cost you anything in the dimension. On the other hand, if you do the same thing we did in 1 dimensions for this heavy tail case, so I only assume the covariance exists, then the best I can do is apply Chebyshev, and I get this kind of tail. The probability of a deviation of order t is decaying like d over t squared n. So this is worse now in 2 ways. The same as in the one-dimensional case, you get an inverse exponential versus inverse polynomial. But also now the tail depends on the dimension here, which it doesn't for the Gaussian case. Okay, so this is bad news. And we might as well ask this same question as we did in the one-dimensional case. Can I match what I could do for Gaussians under the much weaker assumption that only the covariance exists? So this is now a pretty remarkable theorem, and it was proved only last year by Gabor Lugosi and Shachar Mendelssohn. They proved the analogous theorem for the high-dimensional case. Okay, so they showed, again, for every, I have to commit to my confidence ahead of time, and I'm going to stop saying this now because it's going to be true for the rest of the talk. It's information theoretically necessary. If I commit to my confidence ahead of time, then I can design an estimator, family of estimators mu hat t, such that the probability they suffer deviations of order t plus this dimension-dependent startup cost is decaying like at the sub-Gaussian rate, e to the minus t squared n. And this only assumes that the covariance of this random vector exists. Okay, I said I equals identity, but if it just equals sigma for some general sigma, and everything here has sigmas in the appropriate place, it's no problem.
And the constant in the big O is necessary?
Good question. We don't know.
Might be one.
For this estimator, it's definitely not 1. Oh. Maybe you can do better. I don't know what the information, maybe the information theory says it has to be bigger than 1. I'm actually not sure. I'm not sure this is well studied.
So what is the d over n square root of d over n with? How do is this small in comparison to t?
So, I mean, the theorem is interesting almost for any t. I guess a nice litmus test is to think of the case that the 2 terms are comparable. And that says that when the 2 terms are comparable, you're getting an estimator with deviations of order root d over n, and the probability of success is like e to the minus d.
1 minus e to the minus.
Yeah, 1 minus e to the minus d. Whereas so it's exponentially good in the dimension. Whereas if I did that, if I set the same deviation magnitude for the empirical mean, I would only get large constant probability. Okay, so I'm boosting large constant probability that I would get from empirical mean to 1 minus 2 to the minus d if I want deviations of root d over n.
Okay, and I assume we know that this needs to be there, this curve.
The root d over n has to be there. Yeah. That's there that's there for the Gaussian. Like even if things are Gaussian and like that's information theoretically necessary. Yeah. Good question. Others?
If you want several t's and not only one, not for all t's.
You can get some uniformity over t. I don't know the exact answer to that. You can get some uniformity over t. In particular, even the estimator that proves this it sort of degrades gracefully for t prime that are less than t. It doesn't give you literally this thing. It gives you some other inequality that depends on how far t. If this t and this t don't match, then there's some other term that shows up that depends on the distance between the t you were shooting for and the t you actually used. But it is understood how this decays. Okay. So the main contribution of this paper from last year is some new, very combinatorial notion, which we're going to see later in the talk, of a high-dimensional median. As Pravesh noted, medians are somehow key to this whole operation of achieving very high confidence when you have a lot of outliers. And to design an estimator that achieves this, you have to design a good median. And that's what they did. The problem is that their median is very complicated, and any naive way that I know to compute it requires time which is scaling exponentially in the dimension. So this leads to the natural question, can you achieve this guarantee in polynomial time? And that's the main result of this paper, of this talk, which is that you can estimate the mean with sub-Gaussian confidence interval width in polynomial time. So there's a polynomial time algorithm that achieves this guarantee.
The same mu t between both of them? Or?
No. I mean, in some sense, they're all the same mu t because they're all approximating the mean. So they all have to be close to each other. But no, it's not going to be a direct effort to compute their thing. We're going to be inspired by their estimator, but we'll design a different algorithm.
So in some sense, you could have expected even a polylog t dependence, but the dependence on t is polynomial.
Good
t
question.
Is just a number, right?
T is a number, yeah. So this is an unfortunate feature of the slide design. What you should really think of is being given your confidence, not being given your confidence interval width. So I tell you delta. And now t is actually log 1 over delta. So I tell you delta, it takes log 1 over delta bits to represent that. So if you want to be really persnickety, this is polynomial in the size of the input.
Okay.
But yeah, in a moment we're going to switch to not talking about t, but talking about delta. Okay. So let me show you a little bit of prior work. People have been estimating the mean for kind of a long time, so I can't be totally exhaustive. And I want to make this disclaimer one more time that in this table I'm going to show you, I'm going to talk about tail bounds. It's not, strictly speaking, correct to talk about tail bounds for these estimators because these inequalities only hold at one point in the tail. This is this committing to your confidence ahead of time thing. But nonetheless, it'll let us compare things quantitatively a little more easily. Okay, so as we discussed, if you use the empirical mean, it works great in any dimension. It runs in polynomial time, but its tail bound is d-dependent, and it's inverse poly in the desired confidence. We now know lots of estimators that will obtain the sub-Gaussian rate in one dimension, and I'm going to show you one of them in just a second. About 5 years ago, some somewhat more naive generalizations of these estimators were studied to high dimensions, and they achieve the inverse exponential dependence, but they don't address the dimension. Right? So these things have dimension-dependent tails. Last year, Lugosi and Mendelssohn introduced this new notion of a median that they call tournament median, which gets the right tail rate, but it runs in exponential time. And the algorithm I'm presenting in this talk, which I'm calling median SDP, has the right tail rate, works in any dimension, and runs in polynomial time. So just one last time, this is the main theorem I'm going to prove. And I'm showing it this way now in terms of confidence interval width, because I want you to sear this number into your brain. It's going to appear a bunch of times for the rest of the talk. So I give you a list of samples. I give you desired confidence. You can estimate the mean such that the probability you deviate by this much, root d over n, which is this startup cost, plus root log 1 over delta over n, is bounded by delta. Okay? So this number is going to appear over and over and over. I want you to remember it as best you can. Questions about the statement of the theorem?
In some sense, you should think of delta as 1 over d, or?
I mean, it's interesting in plenty of regimes, right? It depends on how much, what your application is. If you're going to need to take a union bound over exponentially many things, like exponential in dimension, then you better think of delta as 2 to the minus d. You know, and if you're going, if this is already beating the existing things, even if delta is 1 over d. If delta is 1 over d, the existing polynomial time algorithms would have had d times log 1 over delta here, and they would have had a d log d, and you're winning by logarithmic factors in this width. Does that make sense?
Why not take delta to be 2 to the d?
Well, 2 to the d is bigger than 1, but 2 to the minus d.
To the minus d, yeah.
Sure, yeah. I mean
there's
if you're
no reason to take it to be 1 over d, right? You don't turn anything.
Yeah, I mean, it'll run, like I didn't tell you what this constant is. It makes it slower, right? The running time depends on log 1 over delta, but yes. Okay. So I think the main algorithmic innovation is some new semidefinite programming-based algorithm to compute a high-dimensional median. This SDP is ultimately based on this sum of squares hierarchy that maybe you've heard of. But you can stay awake because the SOS familiarity is not a prerequisite for this talk, except for maybe the last 2 minutes, in which I'm going to say something about how SOS gets employed. But by some judicious simplifications, we're going to manage to focus only on basic SDP for the rest of this talk. OK, so I want to now do a little bit of actual math, if you'll permit me. But first, are there any questions about this? Any further questions?
So the previous result was just existence without complexity bound at all? Or?
It's pretty clear you can do it in time exponential in D. I mean, I don't think anybody ever fully worked it out, but I think that's not so hard. But you discretize, you do some discretization argument that requires an epsilon net of has exponentially many points. And then I guess I said this on the prior work slide, but the previous polynomial, I can write on this, yeah? The previous polynomial time result would have had this instead of this. So in particular, if delta is like 2 to the minus d, this becomes d, and this stays root d. OK, so the agenda for the next 30 minutes is I'm first going to talk about the one-dimensional case. I'm going to go back to this old theorem and show you how to prove it by this estimator called median of means. And then we're going to describe how Lugosi and Mendelssohn generalized this median of means idea to high dimensions, but this is going to be some exponential time business. There's going to be some serious combinatorial high-dimensional geometry that happen here. And then we're going to describe how to get around these issues in high dimensions to compute things in polynomial time. OK. So median of means in one dimension. What's the setup? I give you n samples, x1 through xn. They're IID copies of some unknown random variable. It's real valued. It has mean mu. It has variance 1. OK? Super basic setup. My goal is for a given delta, I want to give an estimator mu hat delta for the mean, such that the probability of suffering this size deviation is bounded by delta. And just remember that if I used the empirical mean, instead of log 1 over delta, I would have gotten 1 over delta here. So I want to do exponentially better than the empirical mean. Okay, that's the goal. So here's the estimator schematically. Take your samples and put them in chunks. Okay, just the first bucket of samples, the next bucket of samples, the next bucket of samples. And I'm going to use log 1 over delta chunks. Okay, and think in your mind about running log 1 over delta independent experiments. Each of these we're going to think of as some independent experiment that gets me some information about the mean. So inside each chunk, I take the mean. Okay? So I take the average of the first n over log 1 over delta samples, the next n over log 1 over delta samples, and so forth. And I get log 1 over delta numbers, z1 to zk, z1 to z log 1 over delta. And I take their median. That's the estimator. Median of means. So here it is in pictures. I ran it on some data. here's a bunch of samples from the uniform distribution from 0 to 10. I bucketed them and took their means in the buckets. I think I used 10 buckets. And then I took the median. And I got pretty lucky because it's pretty much at 5. I didn't even move it by hand. That really happened. OK. So let's analyze this thing. The key insight in analyzing this guy, I think, is that the number of outliers in a list of samples from a heavy-tailed distribution is much better concentrated than quantities like the sum of outlier values or the average. Sums of outlier values, this is like a wildly fluctuating quantity because that's what it means to be an outlier is you're big. Whereas we're going to see that something like a count is much better concentrated. So here's the analysis in like 3 minutes. It's actually really simple. You might have even done it as an exercise in an algorithms class. If you've read a streaming algorithms textbook, you've seen this. What do I do? So I took my samples, I put them in buckets. I got these bucketed means z1 up to z log 1 over delta. Okay, and these are the dots, the purple dots and red dots. Think of them as IID samples from some random variable whose mean is the guy I want. It's mu. And because I averaged samples, I averaged n over log 1 over delta samples per bucket, I reduced the variance from 1 down to log 1 over delta over n. Notice that there's already a trade-off here, right? As delta, my desired confidence, gets smaller and smaller, I want to be more and more confident, I get higher and higher variance, right? So I'm somehow balancing confidence and variance. OK, so here's a first observation. Since these things have bounded variance, at least with large constant probability, each of them is reasonably close to the mean. So quantitatively, the probability that each zi has distance bigger than log 1 over delta over n to the mean is at most 0.01. Like with probability 99%, a single guy is good. A single guy is an inlier. Think of these purple dots as the guys which were good. So now I'm going to use Chernoff. I'm going to say, look, I ran log 1 over delta independent trials. Each one was a coin flip. It came up good with probability 0.99 and bad with probability 0.01. And this means that actually with probability that's exponentially high in the number of trials, 2/3 of my zi's are good. 2/3 of my experiments succeeded. This is some Bernoulli concentration business. You can prove it by Chernoff, prove it however you want. And now the last thing we have to observe is that the median exactly needs that a majority of my trials were successful. That's what the median needs in order to produce a good estimate. So a fact is that if I have a collection of points on the line, and 2/3 of them have distance at most some number r to a fixed point, then the median also has that property, because the median has to be sandwiched between, say, 2 points that have distance at most r. OK, so this is the analysis. Median of means. We did means to reduce the variance. We did median to boost our confidence. And we beat the empirical mean by some exponentially good amount. Like we got a 1 over delta into a log 1 over delta. Questions? That's the only math in the whole talk, so I hope you're happy. OK. So how would we deal with the high dimensional case? How would we do this in high dimensions? Let's just remember, this is the number that's supposed to be seared into your brain. This is the confidence interval width that I want to achieve in high dimensions. So previously, I had just log 1 over delta over n. That was what happened in 1 dimension. Now I want to add this root d over n and do this in d dimensions. So my goal is to match this Gaussian confidence interval size under only the assumption that the covariance is identity. And before I even suggest to you some algorithm to do this, I just want to jump straight to a big problem. Okay, so first of all, I'm going to do this bucketing business the same as before. That's going to work fine, right? I'm going to take my samples x1 to xn. Now they're vectors. I'm going to put them in buckets. I'm going to average the buckets, and I'm going to get some, variance-reduced samples. Think of the variance-reduced samples as these reddish dots. And now, the analysis I had before, it relied on saying that if I draw a wide enough interval around the mean, that with very high probability, like exponentially good, I capture 99% of the, or 2/3, I guess. I capture 2/3 of these variance-reduced samples. Suppose I try to do that here. Suppose I try to draw a ball around the mean that will capture with probability 1 minus delta 2/3 of these variance-reduced samples. If you just do the math, you will find that the radius of the ball that you need in order to accomplish this grows at this rate, d times log 1 over delta over n. Okay? So any notion of a high-dimensional median that you use, whose analysis relies on capturing 2/3 of the samples in a ball, is just hosed. It will only achieve this rate. It will never achieve this. Okay?
So the right analog is to project along different directions and do your 1D analysis.
Just chill out. We're going to get there. That's what's coming. Yeah. Okay. So just to reiterate this problem, a typical sample is too far from the mean. So the result is that this was the confidence interval version. This is the tail bound version. You pick up an extra factor of d. Bad news. So what are Lugosi and Mendelssohn going to do to get around it? Well, Pravesh has spoiled it for all of you. But they observe you can't ask for 2/3 of the z's, these variance-reduced samples, to just be non-outliers full stop. So instead we have to have a more refined notion of inlier and outlier, or of good and bad points. And their version will be direction dependent. So imagine just a thought experiment. Imagine I have a data set that looks maybe like this, and here's the mean. And now I want to point out that depending on what direction you look at this data set in, which points are outliers and which are inliers changes. So if I project the data into this line, then all of these guys, they fall quite near the mean, and the red points look like outliers. But of course, if I project it in this line, the set of points that look like outliers changes. And this is the intuition, this is the idea that's going to underlie the whole rest of the talk, is that it matters what direction you look in to decide who are the inliers and who are the outliers. So here's the estimator, and it is going to do what Pravesh suggested. It's going to try to mimic this one-dimensional analysis that we gave before in every direction. So as before, you take your samples, now they're random vectors. You take your desired confidence, you put the samples in buckets. You're going to use log 1 over delta buckets, and you take the mean in each bucket. You get these guys z1 to z log 1 over delta. Now let me make the key definition. This is the main important concept for this estimator. I'm going to call it centrality. That's not what they call it, but I think this name is better. A point x in d dimensions is r central for some number r if for every direction you think of u as a Euclidean unit vector, just a d-dimensional unit vector. Every time I project the data in direction u, x is r close to at least 2/3 of the z's. Okay, so there are at least 2/3 good points in every direction according to the centering x. Now, which points those are might differ as I move u around, but there are always at least 2/3 good points. What this implies, in particular, if you want to think about medians, this implies that in every univariate projection, x is distance at most r, or maybe it's 2r or something, to a median. Right? I could always take a univariate projection. I get a list of numbers, and I could take the median. Right? And this implies that x's projection is always close to that median. So, okay, sorry for the poor art, but I'm trying to illustrate here the notion of R centrality. And just to get you some geometric intuition about what the set of central points looks like. So what do I have to do to draw out the set of central points? There's like one constraint for every direction. And I claim that constraint induces a fat hyperplane. So think of the set of R central, I'm going to say why in a moment, but think of the set of R central points as the intersection of a bunch of fat hyperplanes, one for every direction. Here I'm only illustrating 3 of them, but it's the intersection of all of these. Why do you have a fat hyperplane? Well, what do I do to, what is the direction u, what constraint does the direction u impose on the set of R central points? I project all the data in direction u, so that's like normal to one of these strips. And I look at the quantiles of my points, and I look at the 2/3 quantiles roughly, and I fatten them by distance r. So you're not meant to this is not meant to be totally precise, but the idea is roughly that there's one constraint per direction, and they induce an intersection of fat hyperplanes.
And you're literally correct in every direction?
What's that?
So with this analysis, you're within that bound in every single direction, or in most of them?
Every single one.
Okay, so basically you have an oracle that you give it the direction, it will land you in a strip, and the goal is to converge to a small ball.
Are you describing an algorithm, or are you describing an information theoretic analysis?
No, I mean, what it boils down to now is this analysis gives you an oracle, you give it a direction, it puts you in a thin strip.
Yes, that's right.
The goal
That's
is
right.
to narrow yourself down to a
Yes.
small radius ball.
Yes, yes, if you like. That's right. Actually, in the end, the algorithm is not going, we're not going to think about this convex set because I don't know how to, like, I don't know how to, I'm going to need to define a relaxed version of this set in order to give an algorithm that I know how to analyze. But I'm not sure I'm giving a clear enough answer, so it might be cleared up when we see an algorithm.
If you didn't care about running time, that would be easy, right?
Yeah. If you don't care about running time, all you need to do is the analysis. You need to show that this rate is achieved by this notion of median. If you don't care about running time, it's easy.
And if you...
Okay. I mean, there's some probability you have to do, but there's not anything more than that. So let me describe let me now describe the analysis of this estimator. Actually, I didn't really quite tell you the estimator. So we had a notion of centrality. Let me describe things in reverse order. I'm going to tell you two lemmas about centrality, and then it's going to be very obvious what the right estimator is. Okay? So we'll remember the setup. I give you samples. I put them in buckets. Now I have these reduced variance samples, z1 up to z log 1 over delta. And lemma 1 for this estimator, and this is where all of the work goes. This is some relatively serious high-dimensional probability, shows that if you set this number r, this centrality parameter, to this sub-Gaussian confidence interval radius, the number that's seared in your minds, then with probability 1 minus delta, the population mean is central. Okay, so there is a central point, and in population mean is in particular one of them. Lemma 2 is that this is a fact about centrality, nothing to do with randomness, that any two r central points have distance at most 2r. Let's just prove this really quick because it's easy. The proof is by picture. The reason, centrality is great because it quantifies over all directions. So suppose I have two points x and y, and they're both central with respect to some list of vectors z1 up to zk. Then if I want to measure the distance from x to y, what I can do is I can project everybody in the direction from x to y. Right? I chose this direction because distances along this direction faithfully measure the distance from x to y. And now in this projection, x and y have a shared inlier. Right? They're both close, are close to the projection of some z. And that means that they have distance along this line at most 2r, but that means they have L2 distance at most 2r. Okay, so that proves this second lemma. This lemma we're going to get a glimpse at later in the talk, but not a full proof of because it's relatively technical. But now I think at least the slow algorithm should be clear. Right? All you have to do if you want to estimate the mean is compute these z's and then find the smallest r for which there exists an r central point. Maybe you already know the value of r, in which case just find an r central point and output it. So then the big question for the next 20 minutes is, what about running time? How am I going to do something like this efficiently? Right? Because naively, this set of r central points is the intersection of, well, I guess infinitely many fat strips, one for every direction. Maybe if you do a discretization argument, you can get it to be 2 to the d strips or something, but it still seems like a computational problem. Okay, so this algorithm that I'm calling median SDP, from 10,000 feet, you could think of it as an SDP relaxation of the set of r central x's. Okay, now notice the set of r, I said a convex relaxation on the slide. This set is already convex, right? But the problem is it's computationally challenging, and I want an easier to deal with convex set. So this is the 10,000 foot view. What the philosophy, let me be philosophical for 2 minutes. The philosophy behind designing this thing is that you want to design some convex set, which is my proxy for the r central points, such that every step of Lugosian-Mendelssohn's analysis of their estimator goes through for my relaxed r central points, but I somehow end up with a much more computationally feasible set. This is this heart of this proofs to algorithms SOS method for designing learning algorithms. If you've heard of this, but if not, don't worry about it. The remarkable thing, the surprising thing, is that this can be done by using only a polynomial number of constraints. Right? So this set of r central points, it seemed like it was defined using some exponential number of constraints, and we're going to get away with something much more computationally tractable. Okay, so this was end of philosophy. Back to some math. So let's talk about designing a convex set that's actually reasonable to work with and captures this notion of centrality. One feature of convex sets that I typically like to work with if I'm trying to design algorithms is that I should know when I've found a point in the set. Right? I should know when I've won the game. There should be a membership oracle. Right? So if you think about the set of R central x's, even this seems hard, right? How do I know if I give you some point that is central, so it doesn't have many, it has at most 1/3 fraction of outliers among these vectors z1 to zk in any direction, how would I even check that, right, without enumerating over all directions? So the first idea that goes into the design of this median SDP algorithm, and eventually I will tell you the whole algorithm, but the first idea that goes into designing it is some approach to checking that a point is R central. Okay? So here's the lemma. This is an algorithmic version of this lemma 1 that we saw from Lugosi and Mendelssohn. The algorithmic version says that for this same value of R, with probability 1 minus delta, remember they said the population mean is central. We're going to say something stronger. Not only is the population mean central, it's certifiably central. There is some proof. This proof is eventually going to be a matrix. Actually, it's going to be a dual solution to an SDP. But for now, just think of it as a proof, as a certificate that is polynomial size that proves that for every unit vector u, there are at most k/3 outliers among the zi's in direction u. Yeah. OK. So it's going to turn out that actually, because this thing is the solution to a convex program, you can find it in polynomial time. And this means that actually there is an algorithm that solves the following problem. I tell you z1 up to z log 1 over delta. I tell you the mean. Right? We're pretending I've actually already won the game here. You can at least check that you've won the game. OK. So we're going to see how to do that in the next 15 minutes. Yeah, ish. Let me describe the second lemma that goes into the design of this algorithm, but I'm not going to say much about how to prove this one. The second lemma is that actually, once you can do this, once you can certify, you can also search. Right? So if I could certify the mean being central, I can also find a point that's close to the mean. The lemma says there's a polynomial time algorithm that finds a point that is close to every certifiably central point. OK, so this can be proved in a couple of ways, either with some SOS technology, or there's a new paper that proves it with a very simple gradient descent method. But I'm going to say just a tiny bit about that later. So for the remaining time, I pretty much want to focus on this certification problem. Right? I give you the mean. I give you z1 to zk. And I want you to certify to me that the mean has this centrality property without brute force enumeration over directions. Let me skip that. So here's the problem a little bit more formally. Now that we've all agreed, I hope that this sample bucketing thing is old hat. I'm going to stop talking about it. For now I just have some random variable z. It has mean mu, and z has covariance identity. So everything got rescaled. That's all that happened. And the problem is I give you k IID samples from z. I give you this number r. And I give you some vector x. And I want you to either output yes or output I don't know. If you output I don't know, then you didn't make any promises, and you don't learn anything about z1 to zk, r, and x. But if you output yes, then with probability 1, like deterministically, x should be R central with respect to z1 to zk. And therefore, the computation trace of your algorithm certifies, it's a certificate that x is R central. And my goal in order to solve this underlying statistics problem is that for the appropriate setting of R, so this is just the rescaling of the number seared in your head, don't worry too much about it. For the appropriate choice of R, my certification succeeds with exponentially good probability when I gave you the truth, when I gave you the population mean. So just to illustrate this, if I give you these pictures and these data, and I give you this point x, you have to output I don't know, because there's too many outliers in this direction. But if I tell you a point that's in the set of R central points, I'm hoping that with very high probability you output yes. That's my goal, is that with exponentially high probability you can say yes. So to do this, we're going to use some semidefinite program, which I'm calling the Centrality SDP. And when I design semidefinite programs, usually I start with a quadratic program, some optimization problem. This quadratic program is going to exactly capture centrality. So here's the program. It has two kinds of variables. B's, which I think of as Boolean. There are k of them, and they're like indicators for outlierness. And U, which represents a unit direction in RD. Okay? And the program, the optimization problem, it just says, please maximize over all directions and sets of outliers the number of outliers. This just says please be Boolean. This says please be a unit vector. And then all the action is happening in this last constraint. This constraint captures outlierness. And the important point is it's quadratic. So what does the constraint mean? Well, if bi is set to 0, then this constraint says 0 greater than equal to 0, and it's trivially satisfied. But my goal, of course, is to set as many of these bi's as I can to 1. And if I set bi to 1, what this constraint says is that the vector z is bigger than distance r from the vector x in the direction u. So z is like an outlier in the u direction. So if the maximum value of this thing is at most, nothing, okay, is at most k over 3. If the maximum value is at most k over 3, then this point x is r central. Okay? And because semi-definite programs are like, I'm going to take a relaxation of this, and it's a maximization problem. If the relaxed value is at most k over 3, then I still know that x is central. So in totally standard fashion, I'm going to relax this quadratic program to an SDP. If you've taken an algorithms class that did any SDP, you know how to do this. I relax it to some big PSD matrix. I linearize the constraints. This is just what you get. Don't worry too much about it. You could all do it on homework. And let me tell you a glimpse of how you would analyze this thing. So my goal was that if I told you the truth, that you were capable of certifying the truth. I tell you the population mean, and you can know that it's central. And that means that what I have to do is that for some particular quantitative value of r, I have to show that with exponentially good probability, the SDP value is at most, let's say, k over 3. Okay? So the proof of this comes in 2 steps. Oh, I should get ahead of myself. So then I talked about this certifiable centrality business earlier. This means that a dual solution to this SDP, which is some poly d by poly d matrix, is a proof that the mean is central. Okay, so the proof of this, it comes in 2 steps. And I'm going to give you some sketch of both the steps on one slide, and then we're going to zoom out and conclude. There's 2 steps. One is an expectation step, and one is a concentration step. So my first task is to show that the expected value of this SDP is at most, let's say, k over 6. So like this is k over 3. This is just a smaller constant, 1/6. And the tools to do this are reasonably standard. What you do is you relate the SDP value to a certain robust norm of some random matrix. The random matrix will just be the one I get by taking these vectors zi and stacking them up. If you don't know what the 2-to-1 norm is, don't worry. It's like some first moment analog of the covariance, the spectral norm of the covariance matrix, but not a big deal. And then we use growth index inequality to relate the SDP value to this norm of this random matrix. And then we analyze the typical norm of this random matrix by some high-dimensional probability business. The second step is, I think, actually the more interesting one, even though it's the technically easier one. Remember from way back earlier in the talk when we talked about this one-dimensional median of means estimator, and I said that the key idea is that the number of outliers concentrates much better than average of values or sum of outlier values. And the reason is that it's a counting problem. I was able to, I knew that the deviations of any, like if I have a bad experiment, one of my things goes bad, it only affects the number of outliers by 1. This is the reason for this concentration. And the point in this step of the proof is that argument goes through for semi-definite programs, for this SDP. Okay? So formally speaking, this SDP satisfies what's called a bounded differences property. The bounded differences property says that if you have a function of a bunch of independent random variables, in this case they're z1 up to zk, and if I fix all but one of those variables and then I move one of them arbitrarily, move it way off to infinity, if I know that the function value changes by at most 1, then that function is exponentially well concentrated about its mean. That's a fact from probability. Okay? And the point is that the SDP, it knows that by moving one of these z's arbitrarily far, off to infinity, you can only introduce one more outlier. So its value moves by at most 1 when I move one of the z's. And this is what makes it really different from any kind of norm or average or any analytic quantity in these vectors z1 to zk. That's why it achieves exponentially good concentration. So I'm almost done. I'll take like 3 more minutes. I said this already, but just to review what I think are the insights from this proof. So the insight from the first step is that in this heavy-tailed setting, the usual kind of analytic quantities you would associate to z1 to zk aren't very good. And you have to, even when you're going to use analytic quantities, you have to use robust ones. So you have to do things like replace 2 norms with 1 norms. And this is something that SDPs can do. They can compute constant factor approximations to more interesting matrix norms. If you haven't seen this kind of matrix norm, don't worry too much about it. And the other fact is that unlike norms and averages, SDPs are very stable to gigantic perturbations of their inputs. And this causes them to be able to concentrate exponentially well. OK, so zooming out, I just described to you, at least at a high level, how you would prove this algorithmic lemma 1. How do I know that I've succeeded, that I've won the game? If I tell you the population mean, how can you check that it was central? I didn't say much about how to prove this lemma 2. I want to say there are actually now 2 proofs of this lemma in the literature with 2 different algorithms. One of them was the proof that was in this paper that I wrote back in November. And this proof uses a high degree sum of squares program. It uses this proofs to algorithms method. It's technical, but it kind of, in some sense, it turns the crank on the existing proofs to algorithms ideas. And then a couple of months ago, another group at Berkeley showed a beautiful algorithm that solves this problem. And I want to describe this algorithm to you very briefly, just in hand-wavy terms. What their algorithm will do is they will start at some potential center, some guess of the mean. OK? And now they will try to certify. They'll try to use lemma 1. If they certify, great, they're done. Awesome, they got a central point. If they didn't certify, then what it implies is that they'll get an SDP solution to this centrality SDP that has large value. It says there's a direction with many outliers according to this potential mean. So it's not a good mean, but that direction, that tells me a good way to go. It tells me a direction that I can move my current guess and get closer to the mean. This is what I mean by a gradient descent. So they iteratively solve this SDP with different centers until they can certify. And this is actually much, much faster and a much cleaner analysis than this thing. This is really cool.
So what does much faster mean?
I'll show you this slide. So the main theorem for this talk was the first polynomial time estimator for heavy-tailed random vectors that matches up to constants the performance of the empirical mean in the Gaussian setting. As I said on the last slide, there's this kind of hot news that the running time was already improved from input size to the 1000 to something like input size to the 4. And this 4, it's just the time that's required to solve this certification SDP. The overhead on top of that SDP solve is almost nothing. It's logarithmic in the dimension. So it's a reasonable question, how fast can you get? Right? If now the running time is dominated by some simple-ish SDP solve, we know some methods to solve SDPs fast, at least in theory, so can you do it? Even hotter news, just in the sense that it's newer, is that as of last week, there's a new paper. It'll be up on arXiv in maybe a couple of weeks with a sort of union of these sets of people at Berkeley, where we applied similar ideas and built on them to solve some other basic statistics problems in heavy-tailed settings, in particular covariance estimation and linear regression. But there are actually still interesting open problems here, because somehow computational intractability seems to show up here in a way it didn't in the case of mean estimation. And so we're not getting information theoretically optimal results yet, and it's a pretty reasonable question of whether that's even possible in polynomial time. A moonshot kind of question is does any of this have any practical consequence? So you don't expect that SDP-based algorithms you design to solve theory problems immediately yield fast algorithms to do anything in practice, but maybe what we're doing offers some insight about how to deal with high-dimensional outliers that could be useful in a practical setting. So with that, I just want to say thanks for your time, and I'm happy to take any questions.
So this gradient descent based algorithm